All right, moving right along. Boom, 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 boom. Fun and fancy free. We're going to look at one more law on a theory. The law of multiple proportions states that elements can combine in different ways to form different chemical compounds, whose mass ratios are simple whole numbers multiples of each other. In other words, nitrogen and oxygen can form more than one compound together. And when they form more than one compound, those compounds have different ratios. I like to think of it as somebody read the law of definite proportions and decided, hey, I'm going to get myself an easy PhD thesis. And I'm going to say if same things are the same according to the law of definite proportions, then different things must be different according to the law of multiple proportions. And I went to grad school when all the easy dissertations were gone, apparently. But that's really what the law of multiple proportions says. I think the evil chemists who sit around with nothing better than to do to write confusing tests like to make an overly big to-do over the hair-split difference between the law of multiple proportions and the law of definite proportions. The law of multiple proportions says that elements combine in different ways to form different substances. In other words, nitrogen and oxygen can combine in different ratios, and when they do, they're forming different compounds. The law of definite proportions says that every molecule of nitrogen monoxide will have a 1-to-1 ratio between nitrogen and oxygen, and that every molecule of nitrous oxide will have a ratio of 2-to-1. In other words, the same substance is the same as the same substance. Or rather, different substances different ratios, same substance, same ratio. Before we plunge into Dalton's atomic theory, why don't you write down Shakti? Write down Shakti. S-H-A-A-K space T-I. Let me repeat that. S-H-A-A-K space T-I. A chemist named Dalton took the law of conservation of mass, the law of definite proportions and multiple proportions, and then used them to form a unified theory of the atom. Dalton's atomic theory consists of 4 postulates. The first of these postulates says that elements are made up of tiny particles called atoms. The second postulate says each element is characterized by the mass of its atoms. Atoms of the same element have the same mass, but atoms of different elements have different masses. Okay, and this is the first postulate where Dalton had a little bit of trouble. He kind of got this one right. He had a little bit of trouble with this one. This one, he's good on. He said that elements were characterized by its mass. Turns out he was wrong. Turns out that elements are characterized by their number of protons, not by their mass. He He also said that atoms of the same element have the same mass. Well, it turns out that's not always true. Atoms of the same element have the same number of protons, but can actually have different masses. We refer to atoms of the same element with different masses are called isotopes. Like Springfield's baseball team, the Isotopes, the Simpsons. So he was wrong on those two parts. Kind of right, but kind of wrong. He knew that atoms of the same element had something similar. He also knew that atoms of different elements were different, and he was right there. No need to beat up on the guy there. Atoms of different elements have different masses. All right, the next thing he says is the chemical combination of elements to make different chemical compounds occurs when atoms bond together in small whole number ratios. What this is this is a restatement of the law of definite proportions. In other words, water is formed when 2 hydrogen atoms combine with 1 oxygen atom. Drinking alcohol is formed when 2 carbons, 6 hydrogens, and 1 oxygen combine together. Law of definite proportions is basically restated here in number 3 by Dalton. Then last, and perhaps his most brilliant postulate, built on the law of conservation of mass. The 4th postulate states chemical reactions only rearrange how atoms are combined in chemical compounds. The atoms themselves don't change. This is an expansion, so to speak, of the law of conservation of mass. I also like it because what it says is that chemists are essentially people who play with Legos. If you've ever bought a Lego set, you know that you get all these bricks in the box, and you build the thing on the front of the box with those bricks. But then after you're done, you look at the back of the instruction booklet and you'll see all the pictures of all the other things you can build with those Lego bricks. What Dalton is saying is chemists simply play with Legos. They can build whatever they want in a chemical reaction. However, they can't change the number of bricks that they have. All they can do is change the way the bricks are arranged or the bricks are connected. And I call that the Lego principle of chemistry. I'm sure it's going to win me a Nobel one of these days. Why don't you write down Plo Koon? Write down Plo Koon. PLO space KOON. Plo-koon. PLO space KOON. Plo-koon. Two compounds, methane and propane, are both constituents of natural gas. A sample of methane contains 5.7 grams of carbon atoms and 1.9 grams of hydrogen atoms, combined in a certain way, while a sample of propane contains 4.7 grams of carbon atoms and 0.93 grams of hydrogen atoms combined in different ways. Show the two compounds obey the law of multiple proportions. The law of multiple proportions says that different compounds should have different ratios. So we're going to look at and see if they have different ratios. So let's do our methane first. Methane, by the way, has nothing to do with meth. Methane is actually the fancy word for swamp gas or natural gas, the same stuff we burn in our stove. Our ratio of carbon to hydrogen would be 5.7 grams divided by 1.9 grams. Punch that into my calculator here. And it's a ratio of 3 grams of carbon to every 1 gram of hydrogen. We'll do the same for our favorite Hank Hill gas, propane. And my carbon to hydrogen ratio here is 4.47 grams of carbon for 0.993 grams of hydrogen. Wow. Okay, there we go. Seriously, writing with the stylus is hard, folks. So in methane, we have 3 grams of carbon for 1 gram of hydrogen, whereas in propane, we have 4.5 grams of hydrogen for 1 gram. 4.5 grams of carbon for 1 gram of hydrogen. It's different ratios, so different compounds, so the law of multiple proportions is obeyed. Chemistry's easy, life is hard. If the shaded and unshaded spheres represent atoms of different elements, as shown in the drawing 1, which combination of drawings, 2 through 4, represents the law of multiple proportions? All right. In this box right here, I have 2 elements. We'll call them small and big. If I'm wanting to illustrate the law of multiple proportions, I have to find 2 boxes that contain 2 compounds that have different ratios. Well, let's see. If I look at this first one here, I have 3 small to 1 big. Here my ratio is 1 small to 1 big. Here my ratio is 4 small to 2 big. Ratio should be in lowest terms, right? So I should really say 2 small to 1 big. All of these boxes contain different ratios. Since they all contain different ratios, they're all different compounds. Therefore, they're all representing the law of multiple proportions. See, chemistry is easy, life is hard.